Yes. Good morning. I'll talk about this work, mechanical control properties and motion at the nanoscale. I would like to thank the organizers for the opportunity to talk here, and now especially Luis Felipe. And I'll divide the talk in two parts. Each I'll talk a bit about our work we've done in each of these areas. The first one is about controlling properties with strain, and I'll talk a bit about some general work in the field and why it's interesting to study this stuff in nanoscale, in 3D materials especially. And on the second part, which is a bit shorter, and I think there is also less work in this kind of field, I'll talk a bit about controlling motion using mechanical cues. And then I'll have some final remarks on summarizing the talk. So on the first part, controlling properties with strain. Usually when you think about mechanical properties, you think about structural applications. So you want to have a material that is strong, is light, for example. And you can have many applications. For example, if you have a special applications, you want to have materials that are strong and light. Usually you have this kind of tests in the actual stress strain tests, where you apply some increasing stress on the material until it fractures. And then you get some curve like this, stress strain curve, which the type that you get depends on the material that you are testing, of course. But what I'm going to talk about today is not really about getting materials that are stronger, but actually, if you apply a strain on a material, you can control some properties. I think the most a common example are piezoelectrics. If you apply some strain on the material, you can produce some voltage. And in the opposite way too, if you apply some voltage, you can get some strain of the material. And I think this is the most common case. Still in the 3D board, you can find another examples of this kind of controlling properties with strain. For example, this is a more recent work on something they call mechanochromic. And for example, in the top part, you have some fluorescent material, and you put some ultraviolet light. And then depending on how much strain you apply the material, you can get different fluorescent response of the material. You can also make it opaque or transparent, depending on the strain that you apply in the material. But if we go to the 2D board, you can get much more flexibility on of properties with strain, mainly because if you think about semiconducting materials, for example, and I put here two piezoelectrics, you see that usually they fracture with a small amount of strain, 1%, 2%. If you have metals, they're longer polymers, like the previous case I showed, it's also higher than that. But if you go to the 2D scale, you see that most materials, they can withstand very large amounts of strain. For example, here I also put some 2D piezoelectrics, MLS2 and WS2, and you can see that they can withstand very large amounts of strains. So as you have much more large strain range to work with, you can get much more tunability of the properties of the materials. And before I talk about that, I'll talk there are different ways to apply strain to the material. If you only apply one direction, you call that one axial. If you can also apply from two different ways. If you're talking about in axial strain, you can apply in the zigzag direction or in the armistice direction. And you can also apply biaxial strain, or apply in both directions at the same time. And if you're talking about 2D materials, you can also apply in this vertical direction, but not all. For example, I think it would be difficult to think about how to apply strain, for example, graphene in the vertical direction. But many materials like this one that I'm showing, phosphorine, you also actually have some thickness out of the plane. So you can try to pull or compress in that direction as well. And let me talk about what people have done before about electronic properties. And there's a lot of control in that regard. Yes? It could be, but it could be. I didn't work it exactly why it's a bit higher, but it's about the same. But it's worth noting that that's kind of different because The one that I put here for graphene, it's experimental, so there might be some defects. And the one for phosphorine, it's simulation. So, but it's a bit higher, yes. And if you look at the MRS2, it has this kind of structure. You have like in the middle, you have a plane of some metal, for example, molybdenum. And then on the outer part, you have sulfur, or you can have selenium and other materials. And you can see here that by applying biaxial strain, and they apply less than 10% in total, you can get a whole range of conducting behavior from the material. You can get a material that's a direct semiconductor material. You can get a material that's an indirect band gap semiconductor material. And if you apply enough strain, you can actually make it metallic. So they're calling that kind of changing of properties the strain engineering. Basically, if you want to have a material with some property, you can apply some strain to the material, so it will have the exact properties that you want of that. And for the materials, for example, for phosphorine, they try different kinds of strain to see what kind of response that you get. For biaxial, in the case of phosphorine, and the blue one, I think they use GW, which usually has some reliable values of gap. So you can see that you can control the gap from 0.8 up to almost 3 electron volts. So it's a very large flexibility. When you actually, I'll talk a bit about experimentally. This is simulation, so in simulation we can do anything basically. We can, but there are some methods to apply strain experimentally, but you cannot get that high amount of strain. It's usually smaller. But I'll yeah. 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 But for example, one method you can think about that is you put the material on a substrate that's elastic, and you pull the substrate, and then it will pull together. And that's some methods. I'll talk a bit about that later. But if you actually compress in the vertical direction, you can get for phosphorine too, you can get a large amount of behavior. You can go from direct band gap to indirect band gap, all the way to metal, also for this material. So we have very large flexibility of what kind of behavior you can get from the atomic properties by controlling the strain. And if you look at thermal conductivity, this is a work that I found that studies both nanowires and thin films. And you can see that by applying small amount of strains, he gets a very large tunability of the thermal conductivity. And you can actually think that since the strain is so small, you can actually do that with 3D. And the same work also does with periodic structures, and you also get large results. So this one here is not particular of 2D because you can get large tunability with small amount of strain. So you can also do that with 3D. But I'll go a bit closer to what we did in our work. And this is about controlling the pore size. And the idea is, I think in this case, it's pretty simple. You have a material. In this case, they actually manufacture the whole of the material. This is simulation, so you can make the hole that you want. And the idea is basically that if you apply biaxial strain in a material that has holes, it will have to increase the size of the hole because you're applying the biaxial strain. And this is what they do in this work. They apply increasing amount of strain, and they see that the water flow through that hole that they made increases as they increase the biaxial strain. And they can actually use that for filtration because usually the salts that are in water, they're hydrated. They have a large amount of water around it. So the water can pass, but the salts cannot pass, so you can use that as a filtration method. But this is a bit of, you can think about not very convenient because you have to make holes that are a certain size, and you also have to make them the same size. So it might be more convenient to think about materials that have many pores naturally. So they studied this material. There's a CN type of material, and they show that as apply biaxial strain, and we increase in both directions this cell. Of course, the pore diameter will increase linearly, and eventually you can get water passing through these channels, but the salts will not pass. So this can also be, you can think about this as a filter. So, but what you think about is like this. Can you also control the surface energy density? And the basic idea that you can think is that you have the same amount of atoms in a given area, but you're increasing the area of the material. So if you think about each atom produce some amount of attraction, van der Waals attraction around it. The same amount of atoms, you produce the same amount of attraction when you increase the size of the material, but the area is larger, so the energy of attraction per area will decrease. And this is very qualitatively, we show that we can actually do this. But it's interesting to know about what kind of degree can you control that kind of surface energy density. So for example, for that case that I showed, they applied around 10% biaxial tensile strain. So you can think you can get about 20% increase in area. But also that I can get higher area increase than that. And one thing that I would like to criticize about those two works is that they were using non-reactive force fields. And basically, in this kind of force field, you can apply any kind of strain, the material will never break. So that's a problem, I think, with that kind of methodology, especially when you're applying large amount of strains. So in our work, we are going to be talking about reactive force fields so that bonds can break, and we cannot apply a realistic amount of strain to the material. And now discuss a bit about what kind of use can you find if you actually can generate that kind of material. So the material that we are going to study in this work that we've done, and from here on, for a large part of this talk, I'm going to be talking about something that we actually did. We are going to talk about this material, this covalent organic framework, number 1. And these materials have actually been synthesized in 2005. This was the first one. We have two kinds of coffee materials. We have 3D materials like this one. And we have 3D materials. They're pretty similar to metallic organic frameworks, but they don't have the metal. I think the name is pretty intuitive of what they are. They're covalent. They have some monomer that they covalent bond them, and then make a 2D sheet. In this case here, the gray atom is carbon, the B is boron, is in blue, H is hydrogen, is in white, and oxygen is in red. And they have done some work on that, on electronic properties, and also especially a lot of work on outstacking, if you have a 3D material that's made of those 2D sheets. And somebody already studied the Young modulus under biaxial strain, and they found this value. But they never studied beyond the elastic regime, this material. So that's something that before we start talking about how can you use this, how much can you change the surface energy density, we'll talk about the mechanical characterization of the material so we can know what kind of strain can we apply and how it will respond to that strain that we're applying. So the methodology of this work, we use the reactive force field that allows for the breaking of formation of bonds. We're using LAMPS, the MED package. This is a time step that we use in the simulations. And we had some problems with using thermostats and barostats. They were the fracture. It was not happening in the material should be brittle, and had lots of reconstructions. And we tried using the same input for graphene, and we also found that graphene was not breaking as it should in a single step. It have lots of reconstructions, and this was an effect of the thermostat. So we decided to do the thermalization using thermostat and barostat, but to turn it off eventually when we are doing the pooling simulations. And you have to make sure that since you're using NV and you want it to relax because you're using uniaxial strain, you want it to be able to compress in a perpendicular direction when you're pulling the material. We are using only periodicity in the direction that we're pulling, but the other direction is non-periodic. But we made sure to test different lengths of the non-periodic cells, so we are sure that we are not seeing some behavior that's specific for the nano ribbons. And we apply this strain rate that I'm describing there. And also in our work, we are applying uniaxial strain. So this is the geometry before we can actually perform the pooling. We would like to see how well the React describes the geometry. So we compare that with DFT. And this is the cell that we minimized with Reacts. And after we thermalize that, we actually see some rotation of those rings.
And I think it's somewhat close. It has about a difference of 3% between DFT and React on the size of this supercell that we're using. And it's important to, you see when you start pulling that the modifications in the microstructure of the material are very important to understand what's happening and to understand how we can control the surface energy density. So we characterize that by this angle here, this angle alpha. So if alpha decreases, it is closing the ring. If it's increasing, it's opening. And this material, if you think about the micro rings, it has a similar geometry to graphene. You have kind of zigzag edges and also have armature edges. So we are using this kind of notation, and we are increasing the size of the periodic cell. And once again, this direction is completely non-periodic, so it's completely free to compress if it wants to when you apply some kind of a strain. And when we first got the results, we thought it was kind of strange because the Young model was pretty low, especially if you compare the literature for this material for biaxial strain. It's most 1 of magnitude smaller. So we actually tried to do some tests with DFT to see if it was a problem with the potential. And it's pretty close in this initial region. The MED that we are doing with Reacts and the calculation we do with DFT. So why so much difference between the uniaxial results and biaxial results? And if you look at dynamics, you can have some idea of what is happening and why it's so different. So as you can see, as we start pulling the material, it actually starts closing down. The microstructure changes drastically, and eventually it will break. But if you're pulling in a biaxial direction, you cannot have this kind of closing because you're pulling both in the vertical and the horizontal direction. So if you actually compare this angle alpha with and I'm plotting here in blue, the changes in this alpha angle as you increase the strain in the material. You see that there's kind of two regimes in this kind of in this curve. In the first one, it can actually close these kind of rings, so it can suffer some strain without having a large energy cost because it can deform the microstructure, and this has lower energy cost than actually stretching the bonds. But eventually these rings will close, and you actually have to stretch the bonds, and this is the 6 energy to do that. So in this case, when eventually you close the rings, you have a stronger resistance to the applied strain. And you can see this is the regime 2. And we calculate the correlation between the stress curve in red and the alpha angle in blue. And one of the co-authors calculated that and found this value. The negative sign indicates that when one increases, the other decreases. And what she said is that typically when the correlation is above 0.7, it's a strong correlation between the two results. For some of, as I said, we tried different directions and different Ys of the non-periodic direction. For some, we found the correlations as high as 0.955. So we are pretty sure that this kind of result is this kind of change of microstructure is the reason why the Young modulus is so low for this uniaxial strain. At the specific? Mm. Oh, this one here, because eventually it will close down, right? When it changes here, the specific value that it changes is when it cannot change anymore this angle. Like it's already in this region here, it's already like as close as it can get. So from there, it cannot close anymore the microstructure, and it's basically stretching bonds. So the results that we get, this first part here, the Young modulus is quite low, 20 for a 2D material at least, 20 gigapascal. On the second part, it's much higher, 164 gigapascal, which is actually pretty close to what they found using biaxial strain. And the maximum strain that we got was 0.365, and the maximum ultimate tensile stress was 27.9 gigapascal. Oops.
And just in passing, the material has anisotropic mechanical properties. If you applying the strain in the armchair or zigzag direction, you get very different results for the Young modulus and also for the strain and stress. So we are characterizing the material, so we can go to the second part that's talking about how much you can control the surface energy density with this kind of approach. And since you are closing a lot of you are applying some strain in this direction, which I call in here the y direction, and you get some response in the x direction. And you can see that actually the response is much, much larger than the strain that you apply. For example, if you apply a strain of about 0.25, you get a response of about 0.5, so it's twice as bigger the response than this applied strain. So you can get a decrease of up to 37%, which is quite large. In order to see how much that would modify surface energy, what we did was we got some graphene, and we calculated the energy of the graphene far from the surface, and then close to the surface. And we did this we were getting some frames from the MD Dynamics, and we were doing this kind of process for different frames. And what we see is that the energy does change a lot. If we calculate this, the interaction between the graphene and the COF, it goes from around 6.5 electron volts up to almost over 11 electron volts. So the interaction energy between the graphene and the COF increased by 70% up to that amount. So how can you kind of use this kind of controllable surface energy to do anything? So this is a basic idea. This is like a proof of concept. But if you think about the 3D, if you have a tweezer, you apply some mechanical strain, and then you pick out small material, and then you can drop it off if you just release the stress. So the idea is try to do the same thing, but on a much smaller scale. And this is a video of that. At the beginning, the top COF is closed, and the bottom one is open. So at the beginning, the interaction is stronger with the one that's on top. So if it's closed on the top and open on the bottom, if you move it down, it won't transfer because it likes to be with the one that's on the top. If you do the opposite, if you open the top one and you close the bottom one, and you do the same process again, now the interaction is stronger with the one that's in the bottom. So if you try to pull it up, it will stay there. So you can think of this like a nano tweezer, like if you can pick up and release the object by applying some control amount of strain. And I'm using two COFs here, but you can think like if you have a substrate that has an interaction with graphene of about 9, you can also pick up and drop off as you want, because if you want to drop it off, you just open it will go to 6, the interaction, and then it will stick on the substrate. If you want to pick it up, you just close it, and it will go to below 11, and you'll be able to pick up again. And this is based on a different work on the literature. This is not my work. But the idea that those guys had was you can open and close a nanoscale of graphene. And the idea of the guys was that if the interaction with the substrate was stronger than with, at the beginning, if the interaction between graphene was stronger than with the substrate, so the graphene likes to be with itself, so it will close down, because interaction between sheets of graphene is stronger between graphene and the substrate. If you have the opposite, it will actually roll, it will open, because in this case here, the interaction between the substrate and the graphene is stronger than graphene-graphene. So it will want to increase the contact area with the substrate. And since you can control the surface energy by pulling the material, you can also think about this kind of actuator by using this tunable surface energy density. So going about the methods that you can use experimentally for applying strain and how big can you get this strain. And the first method here that I'm talking about is one that you put the 3D material on top of a substrate and you bend it. So as you bend it, the area on top will get tension, and the one on the bottom will get compressed, so you can apply some kind of strain in the material by bending the substrate. The second one I already mentioned is that you elongate the substrate, and if you elongate that, the 3D material will follow up to some point. There are other methods to do that. You can use, again, piezoelectrics. So if you put some voltage on this piezoelectric substrate. It will expand or constrain or contract. This laser here is for the measuring Raman in this experiment, so it's not really important here. The important part is that they apply some voltage and they compress the material. And you can also use thermal expansion. So if you have a substrate that expands thermically a lot, like PDMS, and you heat it up, it will expand much more than the ones on top, for example, AMRS2, and it will actually create some extension, some tension on the material. And if you want to create some inhomogeneous strain, you can actually apply some local heating. So only this region will heat it up, and the strain will be localized on a particular region of the substrate. But the kind of strain that you can get, it's not that high experimentally. I think up to 4%. But I think that for this material in particular, it might be a bit higher because the thing that limits, it's not that the substrate you only increase by 4%, it's elastic, you can pull a lot. But eventually it will slip, right? The 3D material will try to keep up with the substrate that we're expanding. But eventually the strain energy will become very high, and it will eventually slip from the substrate and will not increase as much the size as the substrate will. But since the initial part of the material, since the Young modulus is low, this can actually be an advantage because you can increase the size of the material, you can apply some strain in the material without as much energy because the Young modulus is low. I'll talk a bit about the second part. That's about controlling motion. There's also some work, but it's kind of different. But it's also interesting that you can control motion with mechanical cues. And I would like to give an idea of how difficult it actually is to move stuff in the nanoscale. And I think I really like this. IBM made a video with atoms. So they put a copper surface, and they put some CO atoms on top of the surface. And they actually made a movie. I think it's a boy and his atom. So they were changing the position of those atoms that make the boy and that make the atom. And they were making different, they were taking snapshots. And they organizing the snapshots into a movie. So they used 242 images to make a movie of this boy and his atom. But if you look at how long it took to do that kind of movie, it took 4 researchers, and working 2 weeks, 18 hours days to produce this kind of video. So nowadays you actually have very good control of where you want to put your atoms, but the time that it takes and the effort it takes, it's pretty high. So 2 methods you can do that of controlling where the atoms are. You can use, for example, an AFM cantilever, or you can use an STM tip. And if you also think about the energetics of this process, efficiency cannot be good, because you're moving an object that's very, very small, and you're using a whole microscope setup to do that. So the amount of energy that you have to spend to do that, it's insane. So you want to actually move objects in a nanoscale, but the idea thing would be if they got by themselves where you want them to be. And if you think about the biology, this happens all the time. So the cells move themselves, and they get where they need to be. And one way they do this is by using mechanical cues. For example, they call that one duotaxis. So let's say that you have like some, hopefully not some heart attack. So it will create some fibrotic scar on the material. It becomes a stiffer tissue than usual. So the cells, those cells here are stem cells that are circulating on the blood flow. And you want them to eventually concentrate on the stiff tissue so they can actually move out of the bloodstream and get into the tissue. And usually what they found is that cells, they move to directions of higher stiffness. So if the stiffness of the substrate is higher, they move in that direction. If it's softer, they won't move in that direction. So where they have that accident, you have some fibrotic scar, it's stiffer, so the cells will concentrate, move away from the soft tissue to the hard tissue, and eventually they will enter the cells. And they actually did this kind of build some kind of substrate that has regions with higher stiffness. For example, here, this is square that I'm putting there. They designed this substrate with squares that are stiffer than the rest of the substrate. And you can see that the cells themselves, they will get to the region where you want them to be. They will move to the region that has higher stiffness. So you're not spending energy, and you're not having to control them one by one, they remove themselves and they will get there where you want them to be. So somebody already did this work, unfortunately, of using this kind of a mechanism of increased rigidity to move some object. So they put some, they have some graphene on bottom on top, and they are bonding these atoms of the bottom graphene, the substrate, to some coil, and they increase the stiffness of the coil as you go along the substrate. And if they see that it's just like cells, the graphene will move to the region that has higher stiffness. And I think it's pretty interesting how they explain that kind of effect. Basically, they measure the interaction energy, and they found that interaction energy is lower when you have higher stiffness. And the reason that they found that is that you have some fluctuations. So we have some distance where the interaction between the mover and the substrate is highest. And if you have fluctuations that are large, it won't be, that kind of average interaction will be weaker because they won't be as that close to the ideal distance or the interaction is maximum. If it's soft, it will fluctuate a lot, so it won't be as much as attractive. If it's rigid, it won't fluctuate as much, and you have good attraction. So what else can we do to try to control motion? Using, again, mechanical cues. And what we're doing here is actually using, instead of using stiffness, we're using curvature to move our taxi that's in red there. Is that, the video, okay. And for this work, we are actually using our non-reactive force field. We're using charm, using the lamps again. We're doing calculation with the NEV ensemble. This is our time step. We tried oscillators and movers, and both work well. And this is the dimension of the structures that we were using in the simulations. And this is one of the simulations. You can see that after it comes out, so it will become clear, but it starts moving up, and then the curvature increases, and it does not like high curvature. It moves out. And as it tries to leave the structure, it will lose contact area with the outer substrate, so it will move back in again. Curvature increases, it will stop and go back again, and this oscillator will keep going on and on. I'll talk a bit about this. If the part that it's moving outside, it does not want to move outside because the contact area will decrease. As it moves inside, the curvature will increase, and it will become... I'll talk a bit about that too. In this case, I'm choosing the kind of nanotube to have very, very little friction. But I'll talk a bit about this later. So this is the energy of along the simulation. So as I'm talked before, when you try to leave the covered region, it will lose contact area, and it will really increase the van der Waals energy very quickly, so it will go back in. As it moves inside, it will keep increasing the curvature, and it will increase the elastic energy. I'll talk a bit about this also pretty soon. So it will increase the curvature, it will increase the elastic energy. Eventually, the elastic energy will become very high, so kinetic energy will go to 0, and it will go back again. If you want to make this, in this case, you can think about this about like a hybrid oscillator, because it's partially driven by elastic energy and partially driven by van der Waals energy. And in this case here, the van der Waals energy is basically constant, and it's moving inside the structure. So it's basically driven by elastic energy and change between elastic and kinetic energy. I'll talk a bit about the mechanism. And the basic idea is that if you have a material, a thin rod, for example, if you want to bend it, you have to pay an energy cost. Typically, the energy cost will be, per energy length, will be proportional to the curvature square. It's pretty intuitive, I think, if you have like any kind of a metal rod and you try to bend it, if you release it, it will just come back again. And the idea of using this kind of spiral is that you have actually a smooth gradient of curvature. As you move inside, it will constantly increase the curvature of the material, and consequently, the energy will increase as well. If you have a gradient of curvature, you also have some force that will try to that will
go against this gradient of energy. And you can basically think about any material that's elastic and any material that has some gradient of curvature, you can use it to produce this kind of effect. And for example, you can try to do the same thing with graphene, and you actually get to do that, and we did this. And if you put some graphene, it will also follow the same principles and also work well. Graphene and graphene. And now talk a bit about the question that you mentioned, why it's not why there's so little friction. And I'm actually choosing the incommensurate orientation. You can see the difference pretty clearly on this movie. If you have if you have a commensurate orientation, it will start moving, but the friction is pretty high, and it will eventually stop, and it will just do some random motion. If it's incommensurate, it will just move on and on. There is very little friction. And the explanation for that, this energy, just talking about the same thing, right? It's driven by elastic energy. As it tries to move out, it will increase the van der Waals energy. But for the, if you have a commensurate orientation, it will become very quickly, it becomes just random noise. It won't be like a not organized movement anymore. And the idea is basically this one. I'm using two graphene sheets here. The one on top has some orientation. The second one has been rotated by maybe 30 or 90 degrees. So you can get from here to here. If I'm stacking two of those layers on top of each other, this is what they call the commensurate orientation. And you can see that there's a clear ordering here. For example, here this is the least energy ordering. That is the AB stacking. So for this guy here, if you try to move the atoms, it will have some energy cost because this is the minimum energy, and you try to move away from the minimum, so you have to pay some cost to do that. If you have these two here, like the one that's rotated and the one that's on the left, and you stack on them, you cannot see any clear pattern. So if you try to move this kind of structure, the basic idea here is that some atoms will gain energy, some will lose energy, but overall there won't be any change of energy. So this is basically moving something in equipotential, so no force needed to do that. And we actually did this kind of surface map. We put some graphene on top of the other, and we move it around the surface. And so we move it a bit up and move again. I think this kind of map here has like 20,000 single point energies. So we move here and move all the way to the left, to the right, and then we move it a bit up and move again, and all the way to the top configuration where it's on the maximum y displacement, and then we move again to the right. And you can see clearly here some maximums, some minimums. The maximums correspond to AA stacking, and the minimums that are in deep blue, they are the AB stacking. For this case here, if you just look at the scale, it's completely different. You have very, very little gain or loss of energy if you move the graphene around the other. And how feasible is this kind of stuff? They can actually make those oscillators with nanotube. They have that experimentally. And they can actually make some nanostructures that are curved. And I think it's interesting that you have this kind of effect, and they call that superlubricity. And it's a huge field of people that work on that stuff. And they showed experimentally you can actually see that. It's not only theory. They have experiments that confirm that kind of behavior, where the friction goes basically to zero. So the thing here that you have, the structures that they have curvature in the experiments, they're much larger. So the curvature gradient will be much smaller than what we have in the simulation. But I think this is not as bad as long as we can put some graphene that has some incommensurate orientation. That should be okay because the friction is basically zero. So even if the curvature is larger, is smaller because the radius of the spiral is much bigger, you still can get some movement because the friction is very, very low. So some final remarks on the first part of controlling properties with strain. And I talked before that 2D materials can support much larger strain values than 3D materials typically, especially if you're talking about semiconductors. So you can actually have a large amount of strain values that you can play with, and you can get a lot of tunability on the electronic and on the light properties of the material. And what we showed in this work is that you can actually control the surface energy if you get a proper material that has some pores, and you can pull it up. And regarding the second part, that's controlling motion of mechanical cues, and it's pretty difficult to get this kind of controlled motion in the nanoscale. So it's pretty nice if you can get some kind of mechanical cues, direct motions so the structure will move itself to where you want it to be. And we show that they showed before that you can do that kind of effect with the stiffness gradients. We show here that we can also use the gradients of curvature to get the same effect. I would like to thank you all for the attention, and also the sponsors and the host institutions that allow this research to be carried out. Thank you.